Hey, good afternoon, everybody, and good morning or good evening, depending on when you're tuning in. And obviously, if you're looking at this recorded, welcome to Cassandra Lunch number 30. Um, coming to almost to the end of the year now. It's pretty much settled that we're going to continue doing this for good. So, really excited about some new developments in Cassandra coming up in the next year. And as we get closer to the end of the year, maybe we can do a year in review of what's happened in Cassandra. Today we're gonna talk about Cassandra and Spark basics, foundations, what you need to know. If you have Cassandra experience, this will be helpful to understand why is Spark important. If you have Spark experience, you'll understand why Cassandra is important in the ecosystem and why together they're really powerful. We'll hint at Kafka, which will be a different topic at another time, about where that kind of fits in. And I'll show some resources that you should take a look at to dive deeper. And there's videos which will get posted on the videos will be, this recording will be posted on YouTube, but then there's also videos that I'll refer to that will be posted on the blog post. So don't forget to subscribe to our mailing list. I want to thank Akwi for co-organizing and helping produce the blog post, get this stuff recorded and put it on YouTube. So we're always looking for help, getting new members and sponsors and speakers. If you want to talk about something, you can become a speaker, talk about whatever you want, as long as in this meetup, it's about Cassandra or something that relates to Cassandra. We're part of a bigger community called Data Community DC, where different groups talk about data science, data visualization, data full stack data science. Night Owls is like a group that gets together and just works on projects at night, moonlighting. We cover Cassandra and things related to Cassandra, things that use the Cassandra protocol. There are no new faces today, so I'm not going to embarrass anybody and tell them to introduce themselves. Group rules, if you have a question, just ask it on the chat, or you can just mention it even, if you want, as long as you're nice, you can interject. We're one of the sponsors at Anant here. DataStax is another sponsor and partner, as well as George Washington University that has given us space in the past, and hopefully they will after the lockdown lifts. We have some local sponsors. Right now, they're just sponsors in spirit because we don't really need anything other than people to show up because Zoom is pretty cheap. And then we have organizational sponsors that have in the past helped us put together things like Data Week DC. They've helped us put pizza and beer on the table at the physical meetups when we as an individual group have not been able to get sponsors. So they're really crucial for the whole community. Data Community DC is actually probably close to 25,000 unique people in the DC area. And when I mean unique, in the sense that there's a lot of overlap between the different groups, right? Any announcements? Okay. You can always subscribe to the YouTube videos and watch them later. And if you're just joining us, there are roughly, I think, 20. All 30 of them are not on because we started recording about, lunch number 7 or 8. And we also have Cassandra.Link, which is a website. It's the best Cassandra knowledge base outside of DataStax, where we hand curate manually without machine learning, hand curate this knowledge, which is credible tools, videos, articles, anything you can imagine related to Cassandra, it's here. A lot of the Spark and Cassandra stuff is also here, and you can search it. Not sure about any specific Cassandra events coming up. We are slated to do a DataStax workshop around Spark and Cassandra. And that code it'll be a hands-on walkthrough, even though we're going to go pretty fast. I don't expect people to follow, but it's basically the third installation of a series called Event-Driven Toolkit. So we talked about Cassandra making an API. Then we talked about connecting Kafka to Cassandra using Kafka streams and just basic Kafka consumer and the Java connector to take data from Kafka, put it to Cassandra. And then this one is going to be about how to take data from Cassandra, process it in Spark, save it back to Cassandra, as well as being able to take data from Kafka and save it to Cassandra. And this is the actual material is kind of getting finalized. Arpan actually was on this call. He's working on the code for that. And actually, when we were doing, because we're talking about Cassandra and Spark, it'd be interesting, Arpan, to kind of get you to talk a little bit about it. So, just maybe be ready with your Visual Studio code or whatever, or Gitpod in that case, and maybe do a quick walkthrough of how you're doing it in Astra, okay? You don't have to do it like in the next 5 minutes. Like I'll give you like 20, 30 minutes. All right. So let's see. Just as a quick, I know that people here have used Cassandra and some people have used Spark. Anybody here used Cassandra and Spark together other than Arpan? I think OB, JB, you've also used it. David, what about you?
Really, most of my experience was at PTO.
Yep.
And now I'm trying to get back into it.
Yeah, totally. JB, go ahead.
I have used Cassandra, Spark, and Kafka.
Great, awesome. And Obi, I know you've done some presentations on this. So looking forward to getting questions from you guys, if not comments and additions to this topic. Zoom out for a second. We, as I have mentioned, have been doing this for a while now. Probably start putting the date in here so it's easier to look and see. There's a bunch of stuff in the backlog. And I do intend on getting to it. Today, we're basically kind of talking about this. So maybe I can cross this off the list. And today, we're going to focus on Cassandra and Spark. So I have, as a general outline, 3 main things I want to talk about and show you the resources. All the resources are here, but I'm going to interject them into each of these topics. By themselves, let's take a look at Cassandra. Cassandra is proven open source technology. So is Spark. Cassandra has multi-region peerless replication. And really should be masterless. But in the sense that there's no, it's a completely peer-to-peer at the data center level and at the region level. In Spark, it's not necessarily, that's not what Spark is for. It's not really doing, it's not going to take work and do it in both places, right? We'll talk about that in a second, why that really wouldn't make sense to do the work twice. Storing data twice makes sense for redundancy. Doing the work twice, well, there may be merit to that. We can use Spark on physical virtual containers, on hybrid or multi-cloud. We can use Cassandra and Spark on both, right? Because it's open source, we can use it anywhere. Apparently, this is not a real word, but Cassandra is massively distributable / scalable. I would even say infinitely scalable. And as is Spark, and it's available on different schedulers. And what I mean by that, there's the standalone scheduler, there's the Yarn schedule, there's the, you can even do it now with you can do it on Mesos, and you can also do it on Kubernetes. And now in DataStax, it's essentially the standalone, but it's using DataStax as the state of the system rather than like one master, right? So that's another cool part of it. Though this seems similar, in its own right, Cassandra is both a transport and a communications protocol. What do I mean by that? When you save data to one data center and you have another data center in which you have replicated the key space, it automatically moves data from one place to another, right? So I really should say this is storage. Right, you store data, and it also can transport and move it to another part of the world, right? In Spark, it's combined processing and streaming. So you can do batch processing, right? And you can do streaming, okay? On the same platform. And then when you combine this with this, you get, I would say, like a full data platform, right? You're able to have data regionally, globally distributed, and you can do certain operations on different data centers in a streaming fashion, in a batch fashion. You know, a lot of amazing things happen when you put these things together. Sorry, I just made a note to myself that I have to update the article that I've written on this to actually make it more accurate. Cassandra is a distributed NoSQL data store. Spark is a distributed computation engine. And we'll see how that distribution of data and compute really kind of come together. And you know, although in the Hadoop world, they would have HDFS for storage and they would have, you know, MapReduce for processing. When Spark became kind of like the next generation of big data, it left behind HDFS, even though it can still work with HDFS. But it opened itself up to various different data stores, including Cassandra. And what it used to have as far as data locality in HDFS, in Hadoop, Spark actually has similar data locality with Cassandra. Cassandra has CQL, Cassandra Query Language. It's like SQL. It's not exactly SQL. Spark has Spark SQL, which is a Hive compliant like SQL. I mean, in the sense that like you can do a lot of SQL type stuff, including joins, right? You can't do joins here. You can't do arbitrary queries, right? Which we'll talk about in a second. But there's a lot of overlap in how people work with Cassandra and with Spark. When I say overlap, it's the needs that people have. Eventually, Cassandra and Spark is the right combination. It's not always the right combination, but in some cases, it's the right combination. When you put these together, what does the best of both worlds look like? So Cassandra with multiple data centers, you can have what's called a translytical platform, where you have one data center for online transactions, and you have another one for OLAP. Okay. This presentation by Patrick, I'm just going to fast forward to the slide that I want to show. So imagine you have you know, one data center where transactions are coming in, your apps are pulling data from an API from a data center here, right? You can have another data center where data is replicated, and you have Spark here operating on this data center, right? We have Spark jobs, and whatever data is processed and saved comes back here. So imagine, let's say an IoT application, right? Systems and sensors are sending data here. It gets replicated to this other data center. Some Spark streaming or a Spark batch job processes it maybe once an hour, updates the roll-up data to this data center, and then that data gets replicated here, and then your phone or your API is then able to retrieve that information. All while this is working at infinite scale, right? Whereas this data center just needs to have enough storage to pull the data. And here's the other thing, even if you don't have Cassandra and Spark co-located here, even if you just had Cassandra as a separate data center and you had Spark outside in another cluster that operates on this without data locality, still the analytical processing is happening here, or saving of data is happening here in this data center, and it's not impacting the workload of transactions over here. You can also, for example, stream data to this data center while you have batches happening here. Right? This is the idea of a translytical platform. I'm not going to advertise DSC, even though they're a partner, but essentially that's what DataStax does. But you don't necessarily have to use DataStax to do this type of separation of workload. Oops. Any questions here? There's an article talking about a global data and analytics platform. It's a 5-part series. And what we do is we talk about, if you wanted to do a full platform with Cassandra, Spark, and Kafka, what would that look like if you did it with completely open source technologies and you built it yourself, versus if you were to use DataStax and Confluent together, what would that look like? And the goal is that eventually you end up with a platform that can run on Kubernetes, because that's really the future. How all this stuff runs on Kubernetes, because now Kubernetes runs on every data center in the world, or can run on every data center in the world. That's for a different day. All right, if there are no questions, we'll go on to the next. So Cassandra data basically becomes available as a core data type in Spark using data locality. Even if you don't have data locality, it'll pull it into memory, and you are interacting with the Cassandra table data as an RDD, as a data set, or as a data frame. As Spark has improved over time, the underlying data store that you operate on changes, and these are all available, even in the newer versions. But at the end of the day, your Spark code is operating in the same way it would operate with, let's say, HDFS data, or with Parquet data on S3. Whatever the data that you're working with, you don't have to change the way you're working with it because it's backed by Cassandra. You're operating in Spark world. It's just the data is backed by Cassandra. That's really the only thing that's happening. You get all these goodies of data locality, and you get all these goodies of translytical processing because of Cassandra, but Spark in its own right is just helping you process and compute information. This deck by Russell Spitzer, who used to work for DataStax, was instrumental in the creation of the Cassandra Spark connector. Spark Cassandra connector. And recently, the Spark Cassandra connector has been given the full power of data locality, even if you use open source Cassandra without DataStax. I think he may still be involved in the mailing list, but Russell basically built this and has been maintaining it. And he was the one who was answering questions on the Cassandra Spark mailing list, or on the Cassandra list about Spark and Cassandra. So you can go look it up, right? You can go use Spark with Cassandra all the way back to Cassandra 2.0. And there's lots of how-tos and stuff right on the readmes of this repo. Anyways, back to this. He has really interesting presentations. He always uses movie references. So I'm not going to go into this, but one easy way he explains is that if you have to do Superman work, you don't necessarily want to get Superman to go to Gotham City to solve the crimes in Gotham City. You'd rather have Batman solve the problems in Gotham City and have Superman solve the problems in Metropolis. So that's the idea of essentially having an executor sitting next to the data, right? And he walks kind of through this about how data locality is essentially taking the tokens of your ring, of your Cassandra ring, right? Breaking it apart, and then those token ranges get broken apart into these Spark partitions, right? And then these Spark partitions are basically, in this case, we're talking about RDDs. This is an older presentation, 2015. Those Spark RDDs exist on certain machines, right? They're not existing on every machine. The Metropolis RDD, the Gotham RDD, the Coast City RDD are going to the machines that have the executors for Superman, Batman, and Green Lantern, for example. And the way it does it, it uses a CQL where this is a table scan, right? This is a table scan, but it's a table scan based on the token range. So it's not as bad. It just does it for that machine, saying, I just want this much data. Give me all the partitions in this range right here. Okay, and especially with vnodes, it doesn't mean like everything on the server, right? Vnodes, there's a bunch of vnodes on the machine. It breaks it apart. So every token range, every virtual token range gets pulled into a different kind of partition. All right, any questions here about data locality and how it breaks it apart? Again, this is an older presentation, but I think it's easier to understand what we're talking about here, to say why we want to move data to one machine, or not even move. That data is there in that one machine, so we can operate on it. Okay. All right. You can go through this on your own time. There's a bunch of videos that I'm going to be referring to. And then I'm not going to do the whole thing. I'm going to just go down to the highlight related to data locality here. So basically each partition gets taken into its own, each range of data gets put into its own node, and that executor then works on it, right? It operates. If you have that Spark process working on the same machine as that Cassandra process, it knows that it just needs to operate on data right there, right? It still needs memory, Spark needs memory, but it doesn't need to keep as much of it in the memory. You can take data in memory, operate on it, save it back to Cassandra very, very quickly. Versus if you were using, let's say, S3, you'd have to pull it into memory, operate on it, save it back to S3 every now and then. And that's a much more latent operation. There's a deck here, which I don't think this is it, but it talks about how the later versions of, it's not quite done yet, but Cassandra and Spark together can be almost as fast as just reading and writing CSVs on a very, very fast disk. For Spark, that's really a big deal, right? To be able to just dump and retrieve data very quickly. Spark does that really well. Now, putting it into Cassandra means that it's in a distributed data store that gets replicated and other people can access it using a different CQL process. All right. Another feature is that once your data is in Cassandra and you have connected Spark to Cassandra, you can access that data via Spark SQL. Spark SQL is not exactly SQL, but it gives you things that CQL does not give you. Spark SQL gets translated into Spark, and with the Spark Catalyst executor, it optimizes it based on your underlying, operations engine. But I mean, and it requires a lot of memory. But what it does do is it gives you the ability to do joins and wheres and that you wouldn't necessarily be able to do in Cassandra. And you can optimize your table structure. So when you're doing these joins, it is powered by the underlying indexes. So initially, if you don't have any, special, how do I say? If you're not doing a scan, by default, if you say, give me this data and you know the primary key, then it's going to use your native index, right? This is your native index. If you have a secondary index, you can use that secondary index via Spark SQL, just like you can use it in CQL. The same with SASE and the same with SAI. It shouldn't make a difference, meaning the predicate of your query, the where clause, is basically being processed by CQL if it can do it. It's called a predicate pushdown. It's pushing down the where down to Cassandra and not reading it all into memory and then filtering it. Because that's what it'll have to do. If you read from HDFS, that's literally what you have to do. If you read from S3, you have to bring all the data in and you have to filter it in Spark. So that works not only in Spark SQL, it also works with the stuff that we're talking about here. But it's kind of cool, right? You can just do a SQL query and it pushes it down to SQL if it can help it. Otherwise, what it does is it gives you all of this, but it can do a filter by token range, right? We looked at that earlier, how it'll get tokens by tokens, and then it will essentially do a filter in memory. But if you can help it, if you can give it something else, it'll leverage the native stuff, and then it will do a filter by, it'll get everything, and then it'll go deeper and do in memory. And then finally, you can do a predicate index predicate push down if you have DSC, where you have all of this stuff, but then you can do arbitrary tokens that are inside the index. I have not tried this with Alessandra, but in theory, it should work. Let's take a look at this deck. The video is also there. It'll be on the blog post. Let's see what I had put for slide 74. There we go. Sorry. So initially, this was powered by the quote, Spark SQL was powered by Shark server, which ran on Spark, which then got executed in MapReduce. But the way it worked was that the Hive parser would process the SQL, it would optimize it, it would make it into a MapReduce, and then that MapReduce function would be executed in Spark. And over time, it became the thrift server, right? And then the underlying storage was RDDs. Then it became data frames, data sets, right? And then and it doesn't really matter. Eventually, you are replacing everything. Like pretty much, thrift server is now all on Spark, and you do these SQLs statements, and it executes it like it's a database, like it's a relational database. And you can interact with Spark SQL not only inside your Spark code, but via JDBC. If you don't know what JDBC is, basically like as you would talk to a database, you can connect to it using Tableau, using any old database manager tool that it supports JDBC, and it works like a database, right? You can connect it to Excel. Any questions about Spark SQL? I think I had something on, yeah, no, I think I meant Spark 38 here. Okay. All right, no questions about Spark SQL. So what are and these are the top 3 things. I mean, there's a lot of stuff that we didn't even talk about. Like Spark has graph processing ability using graph frames. Spark has machine learning libraries. Spark supports Python, Scala, Java, and R. So all that programming that you could do for data science in Python, you can operate on Cassandra data using the data frame API. Recently, there's a thing called Koalas, which is Pandas compliant a Pandas API on top of Apache Spark, right? And what that means is your data, you're operating on it as it's a Pandas data frame, pretty much, but it gets saved back to Cassandra. So yet to be tested on my end, but pretty cool stuff. What happens if you don't keep it in check? There's the bad part too. Just like with any industrial grade technology, it's handled with care. Cassandra is like, it's not even a tractor trailer. Okay, Cassandra is basically like a big barge, right? It's huge. It can handle huge amounts of data. Spark can handle huge amounts of data. It's very, very powerful. In small scale, you don't see the problems that I'm about to talk about, neither in Cassandra nor in Spark. We talked about data skew, how to detect it. But if you have data skew, okay, in Cassandra, it will spill over to data skew in Spark, meaning the worker will get more data on some of the workers because of your fat partitions, or just the way that the data is distributed on the token range. More data is going to come to some of the Spark workers. And that data skew becomes a Spark compute skew. Some parts of the processing of the directed acyclic graph of Spark is going to take longer. And then that means that some of the Spark worker nodes will be busier, which also happens in Cassandra. When there's more data skew, when there's more data in certain nodes, it's busier. It goes down more, right? So the same type of problems happen. Just adding servers doesn't always solve it. There are also Spark compute skews that happen because people just copy and paste code that they've written in Jupyter Hub or Jupyter. Or they copy and paste code that worked on a single node machine, but they've done it in a very procedural way without thinking about the parallel nature of how work is being done in Spark, and using non-functional procedural practices, which are basically bad. Non-functional / procedural programming isn't bad. It's just bad in a functional environment like Spark. What does functional mean? Functional programming is where you can think of like every operation as a stateless operation, like a math function, right? F of x. If you define f of x as x squared, then you can reuse f of x in different places, regardless of what you give into it. And if you think about the whole nature of Spark, it's taking work and it's operating the same code in different workers. So if you don't think about that and you say, oh, do all these operations, but then I want to do this big for loop against all of this information. Well, that forces the data to come onto one machine, right? There are certain operations in Spark that you only do every now and then because you need to. Like in the world of machine learning, there are certain processes you have to bring everything back eventually. Certain type of machine learning, like training, have to be done on one machine. Whereas evaluation can happen anywhere. But that's not necessarily always the case. Most of the time, you can break apart the work. And by the way, this Spark compute skew, hotspotting is kind of like another term for it, right? Hotspotting or data skew or compute skew. This is common in every distributed system. In fact, the moment you have more than one thing that needs to scale, even if you have two nodes, you'll see it. You'll see the skew if you haven't designed it properly. Any questions? Okay. So how do we tune it? Couple of different ways. Generally, you have control over cores, how much memory you give to the workers. You have control over input and output. These are Cassandra parameters, right? Basically, it's MB per second. And then there's also, so there's throughput. And there's also split size, which are MBs. And what does that mean? So cores are when you have a Spark cluster, it's your total number of cores that are available to you, right? So if you have like 50 cores across your cluster, you can say use 10 cores. And then on each core, I want to use 8 GB of memory, for example. So if you're using 10 cores, it's basically 80 GB total that'll be used. Okay. What does that mean? That means you can literally process 80 gigabytes of shit at a time. That's how you're constraining what's happening. Why do we need to do that? Because if you're writing a ton of, if you're writing a ton of data, it's going to make Cassandra busy. And Cassandra can take a lot of hits, but if you don't have a translytical setup with different data centers, then it will put too much strain on the same data center. And you need to kind of back off a little bit. Because Spark will go to town. It will use up every amount of memory if you want to give it on the Spark side, and it will exhaust the amount of resources you have for Cassandra itself. Right. Another way to tune that is through input-output parameters, specifically throughput. How much data should I be handling at a per second basis? And the split size, which is how much data can I get at a particular time from Cassandra, and how much can I send back to it at a particular time? These are two different things. If you're dealing with really, really small rows, your split size can be small. Okay, and it'll go very quickly. But the moment you start having like bigger partitions, you need to have bigger split sizes. Otherwise, it can't even read the thing. Okay. So anyways, we've got our general tuning parameters. On the writes, actually, I should probably talk about reads first. On the writes, you can tune how many partitions you're reading at any particular time. You can break up your queries. And what I mean by breaking up the queries, you can break them up by giving them predicate pushdown or any where clauses. You can do token ranges yourself. I wouldn't recommend that, but there's different ways to break up the queries. And one way would be you scan and you get all the partition keys. And once you have the partition keys, you can then operate on certain, you can parallelize on just that data frame and say, for each of these sets, go do this operation. So you're breaking apart the work, right? That's another way to do it. Changing the paging settings, I mean, this is kind of what I was talking about. Input throughput, what I just spoke about. On the writes, Spark will automatically batch stuff and send it as fast as possible. You can turn off the batching. You can make sure that when you sort data, what this comes down to is like your workers, if you're sorting the data on the Spark side, right, and you're sending it in, it distributes the work evenly based on the tokens where it needs to go to. It doesn't necessarily have to do the sorting operation on the Cassandra side. I have to find a clear, like a tangible example of this. And I might find it and add it to the blog post later. Having enough data in a task, this is important. If you don't have enough data, your Spark is going to be overworking for small amounts of data. And you can always tune the output throughput. So I forgot to put the, here we go. And this one. So this article on Medium actually talks about, Cassandra and Spark, not in the DataStax world, just generic Spark. It talks about, for example, using Cassandra in this multi-data center process, right? Like you have Cassandra connected, You have one part which is running Spark batch on Hadoop against Cassandra. I'm talking about the Hadoop, like the Yarn engine. You have another data center where systems can read data. You have another data center where you're doing Spark streaming. This is a representation of Lambda. And you can use Spark in Amazon's EMR or GCP, Dataproc, which is basically like a managed Hadoop. And they have their own storage engines. It talks about like the benefit of having HDFS, but essentially it walks you through how to set it up, right? It walks you through going through how to read data, how to write data. It talks about the data skew, shuffling, when not to shuffle, right? It talks about you don't need to shuffle. Great article, and it will walk you through all the different optimizations. And here you can see where we're giving it, let's say 20 GB on 100. This is 2 terabytes of memory that it's going to be using here, right? Let's see if there's anything useful here. Yeah, talks about Spark partitions versus Cassandra partitions, why you need to pay attention to it. So write settings, here we go, right? Batch grouping key, group the base on this value, right? Based, right, or the default is the partition. But if you give it some other, key, it will use a different key to repartition those batches. You can also set it to what's called a replica set. Buffer size, okay? Default is 1,000. Batch size rows, number of rows, number of concurrent writes, throughput MB per second. And if you want to look at some of the other tuning parameters, concurrent reads, consistency level. Oh, by the way, didn't mention this. Try to operate off local 1 per read, because if you don't, it's going to slow things down. It kills the whole data locality thing, right? Talked about that. Reads per second, size in MB, right? Split size. Throughput per second on the input side, read side. And on the right side, it didn't show it. Did it show it? It didn't show it, but on the right side, you also have something similar. Where do we go? We'll just have to go to the Spark Cassandra connector project. That's not what I wanted. That's what I wanted. And let's take a look at the docs. No, that's not what I want. I need to see the wiki. Where did they put the wiki? Oh, yeah. Connecting. There's a table, connection parameters, where it talks about everything. Connection parameters, input, and output. So there's both sides to it. Okay. Why do we need to pay attention to this stuff? Here's an example. So Spark is, if you can imagine, it's like infinite power. And it's like Thor's hammer, right? Like you can hit a big thing with it, or you can hit a small thing with it. But that's not the way Spark works. It's distributed. You can use it as a hammer and operate at big chunks of data if you want, at huge speeds. Or you can say, I've got a billion different things I need to do, but they're small. So let me break apart how I use the power that I have. And that's what this tuning is about. So if you have a billion different things, you can't hit Thor's hammer on a billion different things. Right? You have to break that down into small little hammers to do the work, essentially. And just like in Cassandra, we learn how to break apart the data so it's evenly distributed across partitions and evenly distributed across nodes and evenly distributed across data centers. In Spark, we learn to evenly distribute work across different workers. And when we're combining Spark and Cassandra together, that's the goal. The goal is to break apart the work so that the work is not just on one machine, it's happening on all the machines. Let me see, there's a picture that kind of talks about this. Maybe I'm not finding it. Right? It breaks it apart into partitions, sends the data to the right cores. I didn't find it. But here, if I go to images.google and look for Spark Cassandra data locality, almost every one of these presentations explains to you how Cassandra works. You're like, I don't care. I just want to know how this works. There we go. Right? That's what's happening when you have Cassandra and Spark co-located. The processing of that data is happening on that node. That's what we want. We want all the data spread out. And I will also add this to, where's the data locality stuff? Yeah. And of course, make sure that this reference is also available. Okay. And that's it. And I want to say, you know, hey, this is it. This is all you need to know. But this is heavy stuff. It's heavy duty technology. Just like with Cassandra, you don't need to use it unless you need to use it. Spark does a lot of cool stuff. But if you can just do it with Python and it works, you don't need to scale it. There's also several different libraries for parallel processing in Spark, in Python, excuse me, without using Spark. You can just use it, right? You don't have to use Spark to process data in Cassandra. You don't have to. But if you must, it gives you a lot of power. It's, yeah, I just had an idea. It's like I've been watching Marvel's Avengers on Disney Plus, and it's like every one of these things is like, you know, Infinity Stone, right? Cassandra is an Infinity Stone. You know, Spark is an Infinity Stone. Kafka is an Infinity Stone. And like, they really are powerful. You know, you can do a lot of cool stuff with it, but you like, do you really need it? Well, no, you really need this, right? So anyways, that's it. Any questions? Nope. All right. We will call it a day. Yeah, go ahead. David, you had a question?
Oh, no, you're good. I just liked your comparison to the Infinity Stones.
But like, seriously, like the stack, okay, the higher you go with these Infinity Stone thing, right? There's a Spark, Kubernetes, Akka, Cassandra, and Kafka. It used to be Mesos over here, right? This is one of the newer stacks, you know? Over and over again, you'll see this. It used to be called SMAC. Now SCAC is the new SMAC. And each one of these things is kind of an infinity stone, right? So a lot of power here. Cool.
Rahul, just one thing. When we
Yeah.
say reduce the input output, what exactly it means?
1 second. I'm just gonna save this. So, okay. So here. So here's all the input parameters. Okay. This means that it's only going to read.
Sharing screen?
Oh, sorry. I'll share my screen again. So this means that it's just changing the consistency level. This is changing how many rows per second it can read. Or not per second, it's per driver request. So it could be tens or 20. Like if you have a bunch of operations, right? It's how many do I get at any given time? This is to record the metrics. You know, it kind of shows it on the Spark UI. This is a different thing. Reads per second. How many maximum reads per second per core, right? It's unlimited by default. So you could like make this smaller. And then split size. By default, it's 512 MB. That's a lot. That's a half a gigabyte. Right? So you can split up into smaller chunks, essentially. You can make it 64 MB.
That 512, what you are saying.
Yeah. This is the default. Like if you don't set it, this is the default. This is what it's doing.
Okay.
And then throughput per second is the maximum read allowed per single core in megabytes per second. So if you were to make this, even if this was 512, right, it wouldn't go faster than this, right? Or eventually it comes down to this. It wouldn't go faster than this, right? So when it says there's no default, that means it's infinite. It's doing it as fast as possible. Okay. Now, on the right, you have many more parameters, but the ones that are kind of equivalent, right? There's batch size rows. There's also an output throughput per second. So you can read very, very fast, operate, and write slower, or vice versa.
Okay. And these are the parameters to be setting in the Cassandra or
These are Spark. These are Spark parameters. Yeah, these are all Spark parameters given to Spark when you're using the connector, you can give it these parameters. Otherwise, you can't, right? Makes sense, right?
Yeah, understood. Yeah. No, in that case, when we are saying write, okay, it's mainly Cassandra we are doing a write, right? In Spark write operation, how we are doing it?
Well, who's doing the writing?
No, in the Spark, there are some parameters for writing as well. Oh, is it a write or throughput?
So when you have input, it's read. When it's output, it's write. I'm asking a question. When you say Cassandra is doing the writing, but who is doing the writing? Cassandra is just a storage place. You can read and write from Cassandra, but somebody has to do the writing, right?
Okay, I got it. Sorry. Yeah.
Yeah, makes sense, right? It's just Cassandra is doing its own reads and writes on the cluster. Yeah. But Spark has its ability to limit how fast it reads and how fast it writes.
Okay, got it.
Yeah, okay.
Yeah.
Cool. Awesome. Any other questions?
Hey, Raul, I have a somewhat unrelated to this, what we've been going over question, but just looking at my Docker stuff real quick. I was just looking at the studio and the server. What exactly does the studio have? Because it doesn't seem to have Gremlin or SQL shell or anything like that. So what does it have?
It has all of that. Studio, depending on, when you make a notebook, you can say, I want CQL, I want Spark, I want Spark SQL, or I want Gremlin.
Okay, because when I'm just starting up the container, if I do like, SQL shell, it says, I don't know what that is. But if I do that from the DSC server container, it'll start up Gremlin, it starts all that stuff up. So I'm not sure what I'm doing wrong with the studio.
Gotcha. Yeah, no, I connected you with Arpin and Obi. Maybe you guys can set up a time, and it'll be good for Arpin and Obi to kind of like walk you through setting it up.
Okay. All right. Cool.
Okay.
Yep.
Cool. Awesome. All right, folks, we're at the top of the hour, and I have stopped my sharing. Thanks everybody for coming, and we'll see you next week, same time, same place. Take it easy.